is Delio Mugnolo. I'm very glad to hear about, okay, let me see the title. Delio, can you show me the first page so that I will not, yes. So it is on the Ornstein-Uhlenbeck operator on metric star graphs. Please, Delio. We cannot hear you, sorry. No?
Can you hear me now?
Yes, but there is some noise.
Okay. Can you hear me now?
We hear you, but again, also the
Can
noise.
you hear me now, better?
Yes. Yes, now it's better. Yes.
Wait a second.
So, Delio, I do not hear you.
Can you hear me now, Marietta?
Now you.
Marietta?
Yes, yes. Now I can hear.
Can you hear me now?
Yes,
Okay,
but yeah, maybe you can lower down a little bit. Or I will lower down.
Okay. What about now? Is it better?
Now it's perfect. Yes.
Okay, very nice. Okay, then let me see, because now I have some problem with my screen. Yes, so now it's full screen, I think.
Yes.
Okay, so thank you again for organizing this next conference. First of all, I want to apologize with the experts here in this room, because I think probably most of the things I will explain in this talk are already well known. So basically, this is the attempt to develop a first step for a theory of differential operators with unbounded coefficients in metric graphs. So in the case of like Euclidean space, everything I will tell is well known. And everything has been obtained in cooperation with Abdelaziz Randi from the University of Salerno. This has just appeared in a paper in Discrete and Continuous Dynamical Systems. Okay, so just to be clear with our setting and our notation, let me just mention that, like in the previous case and previous talk, we are talking about finite graphs. So we have finitely many vertices and finitely many edges. And we turn a graph, so a combinatorial object, into a metric graph by associating each edge with an interval of finite or maybe possibly infinite length. And this turns a combinatorial object like a graph into a metric measure space with respect to classical distance, so Euclidean distance on each edge, and then just classical path metric on this new structure and Lebesgue measure typically, or maybe some other measures that we will see. So we have a measure metric space. We can define on each edge some differential operator, and this paves road to development of operator theory and partial differential equations on these structures on metric graphs. So in particular, what Abdelaziz and I were interested in was the study of stochastic processes, so one-dimensional stochastic processes on metric graphs. So classical 1D stochastic process is the Wiener process. So it is well known that the generator is just given by this guy. So just second derivative up to a certain constant. And in fact, the metric graphs, Brownian motions have already been studied. So as far as I know, the first who performed this study were Kosvikin, Potov, and late Robert Schrader. And they characterize, for instance, those boundary conditions giving rise to well-defined Brownian motion on graphs and so on. So what we were interested in was actually the issue of studying Ornstein-Uhlenbeck operators. So for those on just one dimension, it is well known that the generator is this guy here. So it's again a second derivative, but with a certain lower order term. And of course, if you are on R or even on R plus, this term is unbounded. And as far as we know, nobody has ever studied this metric graph. So this was our topic. So now observe the following. If you are on, so if B is a non-zero constant, then perturbing the second derivative by a guy like this can be thought of as a second derivative plus a small perturbation if you're on edge of the finite length or an interval finite length. But this is not true anymore if you are on the whole R. So this guy here becomes, of course, as an unbounded perturbation. So new methods are needed. So this is the classical theory on R. We wanted to replicate these problems and these ideas and issues in metric graphs. And so because we need something unbounded, of course, the most natural way of doing so is to just study infinite graphs, where infinite means not in this case that you have infinitely many edges, but that your finitely many edges have infinite length, so that these coefficients can be actually unbounded. So for simplicity, in this talk and in our paper, we were studying simply star graphs, which are the easiest examples in this class. So in particular, we were considering well, classical function spaces. For instance, the LP spaces on this guys, on this metric stars are simply direct sums of LP spaces on semi-infinite edges. So all of them joined at zero at the center of the star. Okay, so if you have just only two edges, so if your metric star is in fact just R, then there are two classical choices for defining, for studying the Ornstein-Uhlenbeck. So first one is just working on L2 of R, so with respect to Uhlenbeck measure. And then you have certain pros and cons. So the good thing is that, of course, the space is very well understood, and you have a nice way of defining this operator by a quadratic form like this. The problem is that this form is not a symmetric one. So even on L2 of R, let alone in LP, you cannot say that this is symmetric, that this generates a symmetric semigroup. In fact, not even analytic semigroup, because the form turns out to be not closed. And also, so you can see that semigroup doesn't have nice properties, and the spectrum is not a subset of R. It doesn't have real, purely real spectral values. So another choice is to change measure, to pass to Gaussian measure, which is this guy here, and study this operator in L2 with respect to this new measure. So the nice thing is that Gaussian measure on R is a finite measure. So we have nice embeddings of LP spaces. The problem is that if you want to work with forms, then you need to study well, to have a good understanding of the form domain. And with respect to this measure, Sobolev spaces are not so nice, but okay, this is now, this problem is now over, because there was a nice famous paper by the Zapchik or in the book of the Zapchik actually in 96, this has been studied nicely. So now Sobolev embeddings are known for this kind of spaces. So let's start with studying just Lebesgue measure. So because we don't have a nice form theory at disposal, how to show well Bosons. A classical way of doing so is to turn up, you can come up with an explicit formula for this semigroup in classical case of R. This is well known, and this is given by this formula here. So it is known that those are fellow semigroups, so you have nice smoothing properties. You even are mapped to bounded continuous functions. You have positive improvement. Everything is nice. And the problem is that Dabraut and Vespri show that actually you have not so nice operator theoretical properties, in the sense that this semigroup is neither strongly continuous nor analytic on either of these nice spaces. You have good smoothing properties, so you have you can show some estimates on the derivatives of this of the orbits. Lunardi and Vespri could prove, however, that these semigroups are strongly continuous if you just restrict or study LP spaces. But still, it was not clear what the operator was till Giorgio Metafune in 2001 showed that this is the right domain of the operator and could prove this growth estimate for the semigroup. So what Abdelaziz and I could prove in the case of graphs or matrix stars is that well, we could prove a similar formula for the semigroup, for the Ornstein-Uhlenbeck semigroup. So it turns out that this is the explicit expression for the solution of this PDE on metric stars. So you see, the first term is very similar to the classical Ornstein-Uhlenbeck terms. It's just some kind of well, drifted motion along each ray of the star. But then you have also some interaction describing interaction term describes what happens if a Ornstein-Uhlenbeck particle touches the center of the star and then scatters. So this is the unique classical solution of this problem, and you can prove that this is actually a CB function. So it's a unique classical solution in the space CB over the star. Let me just sketch a proof. Well, the idea is a bit different from the classical case in RM. What you do is you take the, so F is the initial datum. So you take the initial datum, you use it to determine M, so just as many as the number of rays in the star. So new mu functions defined each of them on a line on R. So you pass from the star to M lines. On each of these lines, you solve the problem on a truncated line. So just on an interval of bounded length. Basically, you can then let the length of the interval go to infinity. And by classical method based on Schauder estimates, you can show that you can converge. But the point is how to do this. So basically, when you have this M corpus of intervals, you use the solutions you patch them together to get the solution on a star, a truncated star, and then on this star you go to the limit. So this is a bit technical, but everything works fine. So we could prove well bosonness in CB. And well, it turns out that you could even define, I mean, the same formula also defines semigroups on LP, and they are strongly continuous, just like you do on R. The problem is that, again, the semigroup is not analytic, and again, the spectrum is ugly. So how to study the spectrum? That was our actually main interest. Well, you could just do like on R, you could just switch to another measure, in particular to a Gaussian measure, and try to work in this new space. So for on R, this is the unique Gaussian measure for the Ornstein-Uhlenbeck process. So in particular, you have this stochasticity formula. Indeed, Fuhrmann could prove that the Ornstein-Uhlenbeck operator is formally defined with this Dirichlet form in L2 with respect to the Gaussian measure. And in this way, you could prove that you have also extrapolation to a nice family of LP semigroups. So this is classical for lines. And then there is this nice paper by Betafune plus Randi and Schnaubelt, where they could even characterize the domain of the generator of the Ornstein-Uhlenbeck process with respect to a Gaussian measure. So what we could do in our paper is to, well, we have been able to define, to prove the existence of a unique invariant measure for Ornstein-Uhlenbeck also on metric stars, which looks very similar to the classical one on lines. And once we have our Gaussian measure at disposal, then we can study the, well, the quadratic form associated with Ornstein-Uhlenbeck operator. So it turns out that you have a nice integration by parts formula, so you can get rid of this well, drift term and come up with this quadratic form here. So observe that this is the integral. It's with respect to the Gaussian measure, not to the bag, of course. What is the domain of this form? Is a direct sum of H1 functions with respect to Gaussian measures in order for this integral to exist. And then we still have to make precise what we impose at the center of the star. And well, we can impose continuity, and we should impose continuity, of course. Observe that the notion of continuity is well defined because we have the metric measure space. So in particular, this is a nice locally compact metric space. We can have a natural topology basically on this guy, on this structure. Okay, it turns out that this form here is a closed quadratic form with respect to this Gaussian measure, and we can characterize the associated operator, which is just what we'd expect. So it's the Ornstein-Uhlenbeck operator. So again, second derivative up to a certain factor plus a drift term. We have, we're imposing, of course, f to be that f is in the domain of the form. So it's h1, so edgewise h1 plus continuity. We need, of course, an operator to lie in L2. We're still missing one boundary condition, and this boundary condition we're missing is, as you could expect, is Kirchhoff-type condition. So just the sum of all flows vanishes at 0. Well, in a similar context, Metafune could prove that for all P, for all P spaces larger than 2, so for all P larger than 2, the spectrum of this operator on R has this structure here. So it's very ugly if you are working not on Gaussian with Gaussian measure, but with Lebesgue measure. So it's just left half planes, and even each eigenvalue in the interior of this left half plane is an eigenvalue. However, several people slowly realized that with respect to Gaussian measure, you have much nicer spectrum. So you have a P independence of spectrum. You have even explicit expression for the eigenfunctions. You can show that the semigroup is of trace class. You can show that we can study better what happens for even for P equal to 1, which is different from the other cases. So in our situation on metric stars, we get something similar. So we can prove that basically the spectrum of A, just like with the spectrum summary of A with respect to Gaussian measure, just like on R, consists of isolated eigenvalues. So to be more precise, we can prove the following. So for all P between strictly between 1 and infinity, the spectrum, so the operator of purely point spectrum, the spectrum is P independent, and for all P between 1 and infinity, it just coincides with the set of negative integers. And we can also say something about multiplicity of these eigenvalues. More precisely, the even eigenvalues have multiplicity 1, and the odd eigenvalues have multiplicity m minus 1. So again, remember m is the number of rays in the star. So in particular, you can just show, study the summability of these eigenvalues, and you can see that for this reason, A is trace class resolvent, so in particular, the semigroup is trace class as well. Let me say something about the proof, which is combines ideas from classical Ornstein-Uhlenbeck theory with some ideas from metric graph operator theory. So the first thing you have to realize is that the Ornstein-Uhlenbeck operator commutes with the rotation operator of this metric star. So in particular, they can be simultaneously diagonalized. So there are 6 that exist up. Well, yes. So you can study what are the eigenvalues and the eigenfunctions of this rotation operator. These are just, of course, simply the just rotation complex planes. So these are the eigenvalues, and the eigenspaces can be seen explicitly to be of this form here. So they are just powers of these rotations here. Now, so once again, so you have well, so the eigenspaces are simply tensor products of L2 spaces with respect to Gaussian of half lines times this rotations. So now, what happens for E0? E0 reduces simply to L2 functions on a star that are even, whereas all other eigenspaces consist of odd functions. And because you have so a basis of eigenfunctions of the whole spaces due to this property of diagonalization of these operators, you can say that the L2 odd functions on the star graph are simply given by the direct sum of all these eigenspaces here. So basically you have reduced the problem of studying the spectrum to study a spectrum in 2 different classes. So you have even and odd functions, and both of them can be nicely described. And now you just have to study the spectrum of Ornstein-Uhlenbeck on for even and odd functions, and then you can see that this reduces to study the spectrum of Ornstein-Uhlenbeck with respect to Dirichlet and Neumann boundary conditions on half lines. And it is not difficult to see that this is exactly what I said before. So you come up with this formula. So for even functions, then you get the for Dirichlet functions, then you get the odd eigenvalues, and then because you have n-1 corpus of this half lines, then you get this multiplicity, and for Neumann you get the remaining eigenvalues. So we have completed the picture and observed that for m equal to 2, then you come back to the classical case of lines, and this is exactly this result obtained in the paper by Metafun and Co. was mentioned before. Okay, I think my time is almost over, so let me conclude by mentioning maybe an application. If you
Delio, you still have 5 minutes, so no problem.
Okay, then I will. Okay, then I will conclude by mentioning an application of these ideas of this theory, which is maybe a different topic. It's about studying harmonic oscillator on metric graphs. So typically, when you on metric graphs, you study simply the free Hamiltonian, so just second derivative. But of course, if you study metric stars, or in general infinite graphs, then you could even think of adding a potential, an unbounded potential, and see what happens. So what we wanted to study is this operator here, which is classically considered the harmonic oscillator and quantum mechanics. So you see you have a second derivative, then you have again bounded drift, an unbounded potential of this form here. And we could prove that this is a self-adjoint operator on L2 of a star, and in particular it generates a trace class and positive sum group, which is exactly what you would expect from operator from quantum mechanics. The idea okay, so the interesting thing is that we can also characterize the domain of this operator, which is, again, what we'd expect is just edgewise H2 functions that additional are continuous in the center and satisfy a Kirchhoff condition. And the proof is something relatively classical, which we actually borrowed from a paper by Metafune on this subject. So he was observing something similar for Ornstein-Uhlenbeck and the harmonic oscillator on R. There is a nice relation that can be taken over by or from a paper by Davis and Simon from the 80s. So the point is that this operator here, just like in the case of R, this operator here is similar to the Ornstein-Uhlenbeck operator on a star. So you can conclude that you have well-positives also in this case, and the similarity transformation is given by this guy here, which is of course a positive operator. So you have a lattice isomorphism between these two spaces. Even if you change measure, nevertheless you can carry over positivity structures from one to the next one, and because our Ornstein-Uhlenbeck operator was positive, even the harmonic oscillator semigroup is positive. So this is what I wanted to tell. There are of course open questions. One thing one probably can conjecture, but we weren't really studying it so far, was whether the semigroup is hypercyclic or even chaotic with respect to the Lebesgue measure. It cannot be, of course, with respect to Gaussian measure, because you have a nice self-adjoint operator with compact resolvent, with first-class resolvent, but the spectrum on L2 with respect to Lebesgue is so ugly that you could have a priori chaoticity. So this would be a natural guess, maybe. And of course, to study further properties of this harmonic oscillator, which are closer in spirit to classical questions for quantum mechanics, perturbation theory in particular. So, this is all I want to tell you. Thank you for your attention, and this is reference to the paper by Abdelaziz and myself.
Okay, thank you, Delio.